All right, good afternoon, class, or is it good morning? I am recording this lecture as I had promised to do, so it will be a little bit longer than the 1 hour that the lecture time will be, but at least I'll be able to get in all of the material that I want to get in for today, right? So our topic is forecasting. We had begun the topic just to take up the time from last class. So I'm going to begin in earnest now. So I'm going to do a little introductory talk and then I will continue on. So forecasting, right? Forecasting is an important part of life. In our everyday life, we're constantly making forecasts and oftentimes without even being conscious of it. When we decide whether or not we can afford to buy something, or I need to be able to forecast the state of my bank account when the bill is due. When I leave my house in the morning, it's raining outside. No. When I leave my house in the morning, in my mind, I'm making a forecast of the probability of rain so that I can decide whether or not to carry an umbrella. And I hope you all took an umbrella this morning. I've got mine. If you're thinking of buying a house, and you know how Jamaicans love a house, I need to be able to forecast many things. For example, my future income, what the interest rates will look like, what house prices will look like in the future, and some of us maybe, the size of your family. And we take all those things into consideration, I hope, before we come to a decision as to what it is that we are going to be purchasing. No, so that's for us. But in business, all firms need to make forecasts of future sales, right? In order to make decisions about multiple things. Things such as production, what the inventory levels should look like, if we should come to UTech and employ new staff members, and so forth. Public companies are also obliged to publish profits forecasts for the benefit of their shareholders. So you find that future sales and profits for a firm will be influenced not only by the state of the firm itself, but by what is happening in the industry, in the economy as a whole. For firms importing raw materials or exporting final goods, the state of the world economy, and boy, wars and rumors of wars about, eh? This means that the firm itself needs to have forecasts at all levels. Although typically a firm will not build its own forecasts beyond the level of the firm or industry, but instead usually rely on publicly available forecasts, or buy forecasts from outside economic consultants. So when you look at perfect value of information, stuff like that, right? So they buy the information from outside. Governments and central banks need to forecast the main macroeconomic variables. You hear the parliamentarians when it's time for the budget in the parliament banging gavels and talking about macro this and macro that, right? A good number of what they're talking about is just forecasts. So they can make decisions about whether or not they're going to jack up the tax on motorists or if they're going to lower interest rates or hike it, right? And some of these forecasts, we as a public are able to access it, right? So then, from all those examples that I iterated there, you can see that forecasts are generally made in order to guide decisions, right? So a good forecast will help us to produce a good decision. Having said that now, what then can we say that a forecast is? Well, if you use the term forecasting itself, it really is about casting data forward, right? Forecasting, casting to the fore, casting data forward is really what forecasting is. So basically, it is a projection based upon past data, or it is an estimate of an event which will happen in the future. So basically, man is trying to peer beyond the curtain of time to see what's up ahead. Nobody likes uncertainty, right? So forecasting the variables that the company needs or the individual needs is really trying to peer into the curtain of the future, right? Some persons don't leave their houses in the morning unless they hear their horoscope, right? The horoscope is seeking to tell them what is up ahead in the day, right? So then I've said quite a number of lay the foundation to show that every aspect in this life has some element of forecasting. In scriptures, prophecy is forecasting. For those of you who are in the spiritual realm, prophecy is about forecasting, telling the future. Now, why do we need forecasts? We'll see. When there is a time lag between awareness of an impending event or need and the occurrence of that event. So we know we need to plan for the future. Well, we're in the now. So there's a lag between the now and the future. How are we going to deal with the future coming up? Well, forecast will cover that lag in the time that the awareness now that we need it and the then when we need it, right? So this lead time is the main reason for planning and forecasting. No, planning is the fundamental activity of management, and forecasting forms the basis of planning. So a second reason why we need forecasting is to enable management to undertake its fundamental activity, which is managing. To manage, you have to know what you're going to manage, not just for the now, but for tomorrow, the day after that. How will the manager know what to plan for the day after that? They're going to have to estimate. They're going to have to cast forward the data that they think they will need to make plans to meet tomorrow being any time in the future, right? Also, we need forecasting because it is essential for the organization to know what level of activities one is planning before you go and make an outlay of investment. Investment usually here means capital, resources, borrowing, etc. Right? Now, having said that, what are the types of forecasting that we can encounter? Well, we have what we call short-term forecasting, and we have long-term forecasting. Short-term forecasting is usually covering less than 1 year. So for example, those of you who do operations and you're doing materials requirement planning, scheduling, and so forth, budgeting, and the accountants, you can do short cash budgets and so on. Then you know that those data usually are for a year or less, right? So we call those short-term forecasting. And then you have long-term forecasting, and that is for forecasts that cover 5 or more years. For example, your sales and advertisement budget, product diversification, etc. Now, forecasting fall into the models, the basic categories of forecasting methods. We have 3 main categories of forecasting methods. And yes, I deliberately skipped over the elements of forecasting, right? You can read that all for yourself. So the basic categories of forecasting methods, we have 3 broad categories. We have what you call the time series methodologies, and we call those extrapolative. And we have what you call the causal or explanatory, and then you have the qualitative. So you have, usually we will say you sometimes in some headings you will see quantitative and qualitative, where under the quantitative you will have both the time series and the causal. and then you'll have qualitative on the other side. So in some instances, you will simply see two categorization with a subdivision beneath the quantitative. So in some books, I'm just saying that when you go to some books, you may not see it listed as A, B, and C. You'll simply see two branches, one say quantitative, one say qualitative, but under the quantitative, you will see both time series and causal, right? Either way, it's pretty much the same thing they're saying. All right, so here, time series methods and causal methods or explanatory methods are quantitative methods, which pretty much is what I just said. And judgmental methods are qualitative methods, right? In the quantitative methodologies, we use that when we have sufficient quantitative information and little or no qualitative information available, right? And of course, the opposite is true for the qualitative. No. The most basic quantitative method or methods fall under the time series methodologies. So basically, as the word says, time series, it really simply means that you have recorded a set of data over time from past happening. So normally we give you a table of what we call actual data points, meaning these values have actually been observed over time in the past. So we use those actual observed values that we have gathered over time from the past to try and predict the future based on those pieces of data that we've collected from the past. Now, you must be aware then that since we're collecting data from the past over time, that time series then relate to only one factor, time, right? Time. So in order to do a time series forecast, we use methods such as moving averages, exponential smoothing, and a trend line. Now, they are studied at different levels of difficulty, but here we're going to look at the most basic level, right? Now, when we're looking at moving averages, the first type of moving average that a student will encounter, sometimes without even knowing it, is called the naive forecast. We use it. We have something happen today, and we think that, well, tomorrow it's going to go exactly that way. That's a naive forecast, right? To think that tomorrow will look exactly like today. So a naive forecast, a demand in the current time period, is used as the next period's forecast. And I just gave you an example. So for example, you have a business and you sold 10 pencils today. A naive forecast is to say tomorrow I'm going to sell 10 pencils, but if tomorrow is the next time period, right? And time period simply means how we collect the data points, how we record them. Is it day, month, year, etc.? So when we talk about time period, that's just what we're talking about. How is the data recorded? What increment of time? Then you have the simple moving average, right? In the simple moving average, you use average demand for a fixed sequence of time. or periods or time periods. So here we could say to you, find a 3-day or 3 months or a 3-year moving average, meaning each average must compose of 3 pieces of data point. Or we can say find a 5-month or a 5-year or a 5-week moving average, meaning that every time you calculate the average, it must contain 5 pieces of immediate past data point. So when you're doing time series, it's important to note that it's always in the immediate past that you look to find the data. You never look in the current time period for which the forecast, is being calculated. So we also have what we call weighted moving average. The difference between a simple moving average and a weighted moving average is that in a simple moving average, for the number of data points that we request that you use to make the moving average, we assume that implicit in that is the assumption that each data point has equal weighting, equal relevance. Right, but those of you who read Animal Farm, you've heard Napoleon says all pigs are equal, but some pigs are more equal than some. It's kind of same the idea here. Data is important, but sometimes some pieces of data are more important than others, right? So when we're calculating your grade point average, an A is more important than a B, is more important than a C. So the A gets a heavier weighting than the B, than the C. So although all your grades are important, your better grades tend to give you a bit more of a jump in your GPA. Hence, it exerts more influence in your GPA, right? So we know then that all data might be important, but not all are equal. Some are more equal than some, to borrow Napoleon's word from Animal Farm, right? Good. All right. So what does a naive moving average look like? Well, if you look on the board, here you see, doesn't matter what the data represents. There's some orders for anything for 10 months, 11 months, right? 10 months, right? So you have them listed. And so the 120, 90, 100 straight through to 90 are actual orders that were observed in the past. And you want to make a forecast for the upcoming time period, right? So to use the naive forecast, notice that January's forecast of a 120 is used to be the forecast for, so notice that January's forecast of 120 is used to be the forecast for February. And notice that February's forecast is used to represent the forecast for March. So the 120 from February is used, sorry, the 120 from January is used as the forecast for February, and the forecast for February is used as a forecast for March. So we're using the immediate past to forecast for the next immediate time frame. All right. So if we go down to October and we want to do a naive forecast for November, we simply look at what was October's forecast. It is 90. And so that 90 from October, as you see, becomes the forecast for November, right? So that's what the naive forecasts look like. Now, for a simple moving average, we take the number, we specify the number of data points that we want you to use, and we usually call that N. N representing any number of data points we ask you to use. So originally I said N could be 3, 4, 5, whatever number of data points we we use. Now, the data points, usually we write them as DT, meaning the data at a specific time, or DI, which, as I said, are the actual figures that we would have observed over time, right? So let me erase these lines because these lines are coming from the previous slides, right? So if you look at our table, again, it's the same information in terms of the orders that we have used in the previous table. So I'm going to be using this table multiple times. So if you look at the top of the page right here, if you look at the top of the page right here, you said you see SMA. It just means a simple moving average over time. Is the sum of the number of data points that you have been asked to use divided by that number of points. So let me rephrase that. I didn't quite say it right. So the simple moving average is the data for the different time period until you get to the number of data points over the different number of time periods summed divided by the number of data points. So if you look, you see dt n minus 1. So what it means is that the point at which you're going to be forecasting for. So look at the table. You're going to make a forecast for April. It means that when you stand at April, you count 1 and 1, 2, 2 and 2, right down to 3, right down to the number of data points that you pick up, you need to pick up. So notice we pick up for April right here. So you pick up the 100, you pick up the 90, you pick up the 120, you sum them, you divide by 3, and you get that 103. If you're going to forecast for May, then it would be the 75, the 100, and the 90. You sum it and divide it by 3, you get that 88.3. And so you do to complete the table. So when you come down to November now, to forecast for November, here is November, you'll pick up the immediate 3 data points above November. So you pick up October, it's the 90, you pick up September, the 110, you pick up August, the 130, and there you divide by 3 because it's 1, 2, 3 data points you picked up, and there you'll get the 110. So that's the methodology of a simple moving average. Now we have done another one. Well, I've done another one. Oh, shoot. Sorry. So let me get my sharing again, right? I don't know what happened there. So give me a minute. I've gotten back my screen. So we continue on, right? So I was talking about our simple moving average. Okay? So now we're going to look at the simple moving average again, but I am going to look at a 5 months moving average. So we are going to look at calculate an average for June, right? So here is June. We want to calculate the forecast, the moving average forecast for June. So notice we pick up the 110. Here's the 110. We pick up the 75. Pick up next the 100. Then we pick up the 90. Then we pick up the 120, right? So we average that and we get, so we add them up. When I say average, we add them up, the 5 data points, we divide by 5, we get 99.0. And so we go on through the table until we get to October, where we want to forecast for October. So to forecast for October, when we get to October, we'll pick up the 110, 130, the 75, the 50, this 110. We sum them, we divide by 5, and we get the 95. When we want to forecast for November, we can pick up the immediate past 5 points. So we pick up the 90, here it is. We pick up the 110, here is that. We pick up the 130, here is that. We pick up the 75 there. We pick up the 50, we divide by 5, and we get that 91. So notice you can only forecast one time period into the future when we're using moving averages, okay? All right, now note a few things about moving averages, right? I had already said that moving averages tend to assume that the weights for each data point, or the weight for each data point, is equal, and that might not necessarily be so, right? Some data may exert more influence than other data. And if you look at this screen here, you will see that in the blue or purple, I call it purple, right? In the purple, you notice it says actual. So in the purple, and there, that in the purple, you notice it's the actual data that were plotted. And if you look at now the other two lines, it's labeled the 3-month. So there, the pink is the plotting of the 3-month averaging, and the darker red is the plotting of the 5-month forecast. So notice that the pink one, the 3-month forecast, tend to resemble the actual data more in terms of how the graph look, the peaks and the trough, than the 5-month moving average. So then what we can deduce from our moving average is that small values in our moving averages, in this case, the 3-month, tend to capture the data pattern, the actual data pattern, more closely than when you use higher values of N. So the pink line resembles the troughs, the peaks, the up and the downs that occur in the original data than when we use the higher number of data points. So that is true. So that it is important then that we're aware that when we use high number of data points to calculate a moving average, it tends to what we call smooth out random fluctuations that may appear in the data, as you can see in the 5-month, as opposed to the picture that shows you what the 3-month graph looks like. I almost says if anybody has any questions. Anyway, all right. Now, we go on to look at the concept of weighted moving average. Now, so as I said, while the simple moving average implies that each of the data points that we use has equal weighting, in the weighted moving average, a weight is placed on each of the data points that does not necessarily give them equal weighting. Usually the weights that we apply, they should sum to 1. But of course, you're going to see questions where they do not all sum to 1. But usually the weights sum to 1. So here is a simple set of actual information given. So you're given the weekly demand and you're given the weights. See the weights, you're usually given the weights at this stage of the game. So you're given the demand for weeks 1 to 3. You're given the weighting and you're told that the weights are T1 equal 0.1, T2 equals 0.3, and T3 equals 0.6, right? So the weights then must be applied according to the information given. So it means that in calculating this weighted moving average, you're going to apply the weight of 0.6 to the observed value at week 3. You're going to apply the weight of 0.3 to the observed value at week 2. And you're going to apply the weight of 0.1 to the observed value at week 1. Now, one of the differences between the simple moving average and the weighted moving average is that whereas in the simple moving average, you divide by the number of data points, whether it be 3 or 5, in the weighted moving average, you will not divide by the number of data points. You will divide by the sum of the weights. Good. Let me say that again. In the weighted moving average, you will not divide by the number of data points. You will divide by the sum of the weights. So on the board here, if you look at this example, you will see 720 is being weighted or multiplied by the given weight, which is 0.6. The 678 is being weighted or multiplied by the given weight, which is 0.3. The 650 is being weighted or multiplied by the given weight, which is 0.1. Now remember I said that you should divide by the sum of the weights. The sum of the weights being 0.6 plus 0.3 plus 0.1. So in this case, we don't have to show it because the sum of the weight is 1. But what if the sum of the weights is not 1, right? It must be shown. So when we multiply each of the data points by the weighting and sum them up, we get 700.4. And 700.4 divided by the sum of the weights, which is 1, is still 700.4, right? So we don't need to show that the sum of the weighting is 1, because any number divided by 1, well, it's the same number. But if the weights sum to anything other than 1, you must show that division. You must show it in the denominator, because it's going to give you a different answer than what you have at the top. Right? Good. Now, so I hope that is clear. Again, remember, when you're doing weighted moving average, you must divide by the sum of the weights. Well, Miss, why didn't you divide by the sum of the weights? I did. The sum of the weights here, where the weights are 0.6 plus 0.3 plus 0.1, well, that sums to 1. So I'm simply dividing 700.4 by 1. So my answer still is, well, 700.4. But let me reiterate that if the sum of your weights were different than 1, you must write it down and show it, because it's going to impact what the forecasted value will look like. All right, so then we go on to another method of time series analysis, and that is exponential smoothing. Now, exponential smoothing, unlike our simple moving average or simple weighted moving average, does not require so many data points as the simple moving average or even the weighted moving average. With the exponential smoothing, all you really require is the immediate past set of data. You don't need to have a whole set of data points from the past, right? So here, if you look on the board, you will see that we have some symbols. We have introduced some symbols, right? So here we say FT, meaning the forecast for the period under consideration, is equal to FT minus 1. T minus 1 simply means the forecast from the immediate past, plus this little animal here called alpha, where alpha is the weighting factor or smoothing constant. And then you open the brackets, you have dt minus 1, meaning that's the actual demand from the immediate past period, minus again the forecast from the immediate past. So notice that to make a forecast using the exponential smoothing, all you need is a weighting factor that we call the smoothing constant. You need the actual demand from the immediate past, and you need the forecast from the immediate past. All right? Now, note a few things about that little animal that we call the smoothing constant or alpha. So let me just clean off the board so they don't get to the next slide, right? So if you notice, just notice a few things about that little animal that we call alpha. Now, alpha usually lies between 0 and 1, but it can take on the value of 0 or the value of 1. If alpha takes on the value of 0 or the value of 1, those are two special cases. So if alpha takes on the value of 0 and the A is a representation of that little thing called alpha. You can find it in your insert in symbols on your Excel sheet or on your page, right? So if alpha equals 0, the forecast will not reflect any recent data. And if alpha takes on the value of 1, the forecast is based only on the most recent data. So those are two things to note about alpha. There are special cases when you have alpha being 0 and alpha being 1. Having said that, we rarely ever give you a question where alpha is either 0 or 1. But it's important for you to know this knowledge, to have this knowledge, right? So a question then comes up. It says, given the weekly demand data, which of course is on the other page, what are the exponential smoothing forecasts for, and it's asking for the period for period 10. And note it says you're to use alpha equals 0.1 and alpha equals 0.6. So you're going to do two sets of forecasts, one in which alpha is going to be 0.1 and one in which alpha is going to be 0.6. And notice now it asks you a question that was not previously asked of you, and it says, and which is the preferred forecast? We will look at that a little bit more. And which is the preferred forecast? Now, it also tells you that you must assume that the forecast for period 2, so here, where am I seeing all of that? So here is that information. It says to assume the forecast for period 2 here. Assume the forecast for period 2 is equal to the demand from period 1. Now, why do you need that information about an initial forecast? Well, because the formula says you need an immediate past forecast. So it's either you are going to use the naive method to come up with that forecast, or you're going to be told what the forecast is. But you will always need information on the last forecast, as well as information on the last actual observed data point, as well as your alphas, whether it be one alpha you're asked to use to make one forecast, or you're given another alpha to make a comparative forecast. All right? Now, so let's turn to the question. Again, take a little moment to read the question. You're going to be given weekly demand on the next page, and you're asked to calculate the exponential smoothing forecast for period 10. And you're told first, use alpha equals 0.1 to make a set of forecasts. And then you're going to use alpha equals 0.6 to make another set of forecasts. And then you're asked, which is the preferred forecast? All right, so here is your, again, let me just erase those lines because you're coming from the previous page. All right, that's been done. So here is the data that you're given. All right, here's the data that you're given. The weekly demand. So you're given the weekly demand for 9 weeks. So these demand are actually observed, and then you're asked to make a forecast for time period 10. But you're told that the forecast for period 2 you're told that the forecast for period 2 is equal to the demand for period 1, but yet you're being asked to make a forecast for period 10. What that means is you will have to work straight through the data from top to bottom for you to be able to find the forecast for period 9 in order to make the forecast for period 10. Because remember, to make a forecast with the exponential smoothing method, you will always need the immediate past forecast, immediate past from the time point that you need to make the forecast for, and the actual observed demand in the immediate past from the point that you need to make the forecast for. So for example, at point 10, you need the forecast for from week 9. And you need the actual observed value from week 9. Now you do have the actual observed value from week 9, which is 775, but no forecast from week 9. So in order to get the forecast for week 9, it means you have to take the forecast from week 2, which is given, and work straight down through to week 9 to get the forecast so you can make the forecast for week 10. All right, so here I have done some of the work for you. So it says the forecast from the forecast for week 2 is equal to the actual demand from week 1. So here is the actual demand from week 1, and here it has become the forecast for week 2. So I'm going to focus on the alpha equals 0.1 first, right? So here's the demand from week 1. Demand from week 1 equals the forecast for week 2. So here's demand from week 1 being the forecast from week 2. So 820. Now, we have slotted in the information that we've been given, but we now need to find the forecast for week 3. So what do we do to find the forecast for week 3? So if you look below here, where I just put that red mark, F3, we take the forecast from week 2, we plus our exponential smoothing, we open the bracket there, we take the actual observed value from week 2, which is the 775, and we subtract our forecast, from week 2. So notice we're applying the formula. The forecast for week 3 equals the forecast from week 2 minus plus our alpha, which is 0.1. Open the brackets, your actual observed value from week 2 minus the forecast from week 2. So notice that we are only using actual and forecast from week 2 to make a forecast from week 3. So we're using the information from the immediate past to make a forecast for the time period of interest, where our time period of interest here is time period 3 or week 3. So having put that into our little formula and churn it up, you work the brackets first. So 7075 minus 820 is negative 45. You apply 0.1 to that, and that's 4.5. Yes, the plus sign changed to a minus because the plus sign is multiplying the minus, and the minus will therefore stand, as the rule says, plus times minus give you a minus. So even though it started out with a plus sign, you can continue with the plus sign depending on what is in the brackets, but it can change to a negative sign also depending on what the sign in the bracket is. So it's 820 minus 45, which gives you 815.5. So there, that's how we got that 815.5. So when now we come to forecasting for week 4, let me erase that now. So when you come to forecasting for week 4, it's a similar idea. We're interested in forecasting for week 4. So it means that we need information from week 3. So if you look at your table again, the forecast from week 3. So the forecast from week 3 is 815, and the actual observed demand is 680. So to make our forecast for week 4, those are the pieces of information that we need. So the forecast from week 3, which is the 815.5, plus again our alpha, 0.1, you open your brackets. The actual observed demand from week 3 is 680. There it is, 680. We subtract the forecast from week 3, the 815.5. So notice we use our forecast twice, once in the bracket and once at the beginning as you begin the right-hand side of equal sign. So again, you work what's in your bracket first, negative. So 680 minus 815.5, negative 135.5. You apply your 0.1 to it, you get negative 13.5. You do your addition, which in this case turns out to be you're adding a negative figure. So it reduces the 815.5 to 801.95. And so you work through until you come down. So you work through until you come down to period 9, where now you have the forecast for period 9 along with the observed value from period 9 to enable you to make that forecast for period 10. All right, and having done that for alpha equals 0.1, it also asks you to make a set of forecasts for alpha equals 0.6. So you do that all over again, right? So you go to see on the right-hand side of the table. On the right-hand side of the table, you have the start where it says the forecast for period 1. Sorry, the forecast for period 2 is going to be demand for period 1. So that 820 becomes the 820 that you have on the actual demand is going to be the forecast for period 2 on the alpha equals 0.6. And the same way you went through with your 820 plus now your alpha is equal to 0.6 and the actual observed demand of 77.775 minus your forecast of 820. Same way you go through, you get your forecast of 793 for the next time period of time period 3. For time period 4, you use the forecast from time period 3, the 793, and you apply your alpha equals 0.6, the observed value of 680, minus your 793, you work through, you get your forecast of 725.2 right there. And so you work through until you come to the forecast for period 9. Then you use that forecast along with the actual observed value in period 9, and you plug them in, you get your forecast for period 10. Okay? And so you run through the entire periods from periods 2 when you have your first forecast up to period 10. You can't forecast beyond period 10 because you need the immediate past in terms of actual observed and the forecast. So while you have the forecast for period 10, you do not have any actual observed, so you could not make any forecast for period 11, right? So again, it's only one data point into the future that you can make a forecast for when you're using your moving averages. Now, you were asked a question about which one do you prefer? And it says, and which is the preferred forecast? Meaning, do you prefer the forecasts that use alpha equals to 0.1? Or do you prefer the forecast that uses alpha equals 0.6? It's an interesting question. How do you answer such a question, right? Now, when we talk about if you prefer, data points or forecasts. So I'm going to skip to the end because I have it. I shouldn't have put it here, but that's where it came, right? So when we talk about preferences for forecasts, and I want you to listen carefully. When we talk about preferences for forecasts, what we're asking you basically is which forecast is more accurate? That's what you're being asked. So when you're asked which forecast is preferred, the interpretation is which forecast is more or most accurate. Now, having said that, each forecast usually carries something that tells us the level of accuracy in the forecast. So theoretically, when we have made a forecast, we should have accompanying that forecast some measure of the level of accuracy in that forecast. Of course, us being human beings, we don't do something unless we're told outright to do it. So even though theoretically we should have a measure of the accuracy in each forecast, it is only when you're asked the question that you're expected to show that measure that tells you the level of accuracy in the forecast. One such question is, which forecast do you prefer? When you see such a question, what you're being asked to do is to look at the level of accuracy in that forecast, match it to the level of accuracy in the other forecast or forecasts, and say which one has the least amount of error or has the most accuracy in it. Now, what is that measure that we use to determine the level of accuracy in a forecast? Well, if you look at this topic, it says forecast error. When we want to determine our preference for any forecast, we calculate the level of error that exists in a forecast. And that level of error, when we compare them across the different forecasts, whichever forecast has the smallest level of error, that forecast is what is used to be the most accurate and therefore the most preferred forecast. So whichever has the least level of wrongness to it, and that's Jamaican, that is the one that is most accurate, and that is the one that we most prefer. So then, how do we measure our level of error? Well, we do what we call an error forecast, an analysis, right? Now, before we do that, we need to define an error in statistics. A forecast error is defined as the difference between the actual demand and the forecast. I know I have this the other way around here. So an error so the error is equal to the actual demand minus the forecast. And this is how it is written, right? D minus F. The I simply means the forecast for the time period that you're looking at, and the demand, actual observed demand from the time period. So if you're looking at Q3 or week 3, it would be the demand for week 3 minus the forecast for week 3. That's all that means, right? Now, we have what we call metrics that we use the error in a forecast So we look at each forecast relative to the actual demand in the time period for that forecast, one by one. And those errors are used to calculate different error metrics or different measurement of errors. Now we have three different error metric. We have what we call, oh yeah, I've done this again. Give me a second. I want to share about my screen again. All right, so I'm back with my screen. So I'm saying that we have different error metrics, right? Let me go back to the end of the document. I don't know why I put it down there. Right. So we have different error metrics. I already showed you how we calculate the error, the demand minus the accompanying forecast. So those errors are used to calculate one error metric that is called the MAD. The MAD means the mean absolute deviation. Mean just simply average. Absolute simply means that if you take a number, say 6, and you minus 10, the answer is -4. Absolute, which is represented by those two vertical bars, simply means that you take the positive of the number. So your answer will be +4, right? So when we talk about absolute, there are the vertical bars similar to what I have here. So these vertical bars mean the absolute, you borrowed from mathematics. Means that when you get a negative number, you write down the answer without the negative number, you write it as a positive number. So here, over here, there, see I'm putting that mark. The MAD or the mean absolute deviation says that you take each actually observed value, you minus the corresponding forecast, and if you get a negative number, when you do that, you write it down as a positive. You do that for each pair of forecast and its accompanying actual observed data point. So you can't calculate an error unless you have the actual data and the accompanying forecast. So after you have found the error, the absolute error for each pair, you add them up. That's the sum symbol. T equals 1 to n simply means that however many data points there are, you add them all up, and then you divide by the number of data points. Good. So you can use your errors to calculate an error metric called MAD. Or you can use your errors to calculate an error metric called, let me blur up the screen. An error metric called mean absolute percent error, or MAPE. So you can use your So you can calculate the MAD with your errors, or you can calculate the MAPE, or you can calculate the mean squared error. So our errors can be used to calculate one of three metrics. So when you're asked which is the preferred method we do not expect you to calculate all three error metric. We expect you to calculate just one out of the three. And no, you don't get to decide which one you want to calculate. The problem will tell you which one to calculate. So we normally ask you to calculate the one that says MAD. The one that I'm starring, right? So to determine then which is your preferred forecast, you will calculate the MAD for your forecasts. So each forecast that you do, you will calculate a MAD for each forecast, and then you compare the MAD for each forecast, and whichever MAD is the smaller MAD or the smallest MAD, that points you to the forecast that you prefer. So it is not the MAD you prefer. The MAD simply points you to the forecast that you are supposed to prefer. So we are going to go back now to the question that we were asked, and we are going to answer the question based on the use of the MAD metric, right? So let me again take off this star that I have on the screen, lest it be going all over the place, right? So we're going to go back to the question that asks us which of the forecasts we prefer. So here is where we had completed our alpha equals 0.1 and our alpha equals 0.6. So on our next screen, why are you giving me trouble? Good. So alpha equals 0.1, alpha equals 0.6. Let me gently move this. Oh, where did I do that? Give me a second, class. Let me find it. Seems like I did it at the end of the... Oh, yes, here. Sorry. So here is the question that we're answering. Which of the forecasts do we prefer? So here is the absolute error, because remember our MAD says you must sum, I can write it here, right? Our MAD says you must sum the absolute values for a forecast where I equals 1 to n, and you divide it by n, right? So you can't calculate an error for week 1 because you have no forecast. For week 2, it's 775 minus 820. You will get a negative 45, but because it says absolute, you write down 45. For week 2, it's 680 minus 815.5. Again, you'll get a negative, but because the question says absolute, you write down 135. And so you do for the entire forecast of 0.1 matched up against the demand. When you calculate, when you do that, and sum them up, you get 495.32. When you count the number of errors, 1, 2, 3, 4, 5, 6, 7, 8, you divide by 8, you get MAD being 61.92. Now, likewise, when you go to your exponential forecast with alpha equals 0.6, there I'm circling 0.6, you calculate your error again, you go back to your actual demand, you match it against the forecast. Remember, it's the absolute value, 45, again 680, again 793, 113, 655 against 725, 70.2. When you add them all up, you get it. I almost think when you add it all up, you get 546.2. You divide by 8, you get 68.23. So the 61.92 and the 68.23 represents the MAD for the respective alphas. So the 61.92 says that there's an average error of 61.92 in the forecast for the alpha equals 0.1. And the 68.23 says there's an average error of 68.23 in your forecasts of alpha equal 0.6. Now, since the MAD represents errors, the smallest or the smaller MAD will be the better or the best of the lot. Since we're comparing two things, it's the not the est, right? So 61.92 is better than 68.23 because 61.92 is the lower error than the 68.23. Therefore, because the absolute error for alpha 0.1 is lower than the absolute error for alpha 0.6, alpha equals 0.1 is your preferred forecast. So alpha equals 0.1 is your preferred forecast. And that is how you use your error metric to answer a question such as, what is your preferred forecast? Or which forecast is more accurate? Or which forecast will you use going forward? Good. Now I hope that is clear. You can ask any questions when you come to your tutorial if it is that you need additional clarity. But I think that that should be clear enough. So let me clean my screen and let me go back to the point now where we would have a natural continuation of the lecture notes. So what we have done, we have looked at the extrapolative or our time series method in terms of our moving averages. We looked at the naive moving average or simple n data points moving average. We have looked at the weighted moving average, and we have looked at our exponential smoothing. We have also looked at how we answer a question such as, which forecast do you prefer? Now note that when you're asked about which forecast you prefer, that it does not necessarily have to be the same method that you use to forecast one and the other. It could be different methods that are used to make a forecast for a set of data points. So I could have used the naive method. I could have used the simple moving average. I could have used the exponential smoothing. I could have used any kind of formula to make a forecast and ask you which one I prefer. It simply means that once you're being asked about preference, that you are to calculate your stipulated error metric. At this stage, the error metric that you are most likely going to be asked to use is the MAD. Now, we usually have another method that we use under, the time series analysis, but it doesn't look like the averages that we just calculated, it more looks like an equation, your straight line equation, because that is your trend line. Now, so we're going to look at one more method of time series, but I'm going to discuss it along with the idea of the regression model. Why am I doing that? That's because they are both represented by the same equation that we call the straight line equation. So the simple linear trend line and the regression model. So the simple trend line and the regression model are represented by the same equation, y equals a plus bx. Then, Miss, what's the difference? Well, in a trend line equation, in a simple trend line, the x values, which is what we usually call our independent value, is usually some element of time. Not usually, it's always an element of time. Now, this is a review because I know you have done it in statistics or somewhere else. So there's no one in this class who should have been seeing this the first time, unless you have not gone through college math and intro to statistics and so forth. And those things you should have done before you come to decision science. So I know this is a review. So when it comes to a linear trend line, your independent values, which are represented by X, will always be some element of time. Whether that element of time is days, weeks, months, years, you get the picture, right? Whereas for the regression model, there is never any element of time that is represented by the independent value. So I am going to show you what I mean, then we'll come back to that. If you look at this question, I'm always going and not erasing my board, right? So yeah, my apologies there. So if you look at the statement of this, notice that I am asking you about week. Here, week. That's an element of time. And sales, which is some observed value. So if you have weeks, some elements of time, and some observed value, here the instruction must be then, what is the simple linear trend model? Good? So it should be trend because you are plotting some observed value against some element of time. Good? Now, I'm going to show you this information down below. Same information, but with a change in the heading. Good? If only I could get my graph to move, right? Now here, if you look at the values, it is the same values, but notice the heading. The heading says number of competitors in a 5-mile radius. And if you look carefully, the observed values of sales are the same. 1, 2, 3, 4, 5. Around there, the heading was week, but here, no heading of time is here. So in this case, you would construct what is called a regression equation. So when we're talking about regression equation, there's no element of time in the data that you're using, meaning the data that you're going to be analyzing. It's usually some observed values where you have to figure out which is the independent, which is the dependent. But when it comes to a trend line, well, there's always going to be some element of time. So you know that that element of time is always going to be your independent values. So the name of the instruction will change depending on what the heading of the data is, whether it is a trend line or whether it is a regression, simply depends on the information that is in the data in terms of how it is headed up, right? Time or no time. So let's go back to the beginning of the data, right? So I'm saying then, so I started out by saying that both the linear trend line and the regression model are represented by the same equation, which we call the straight line equation, y equals a plus bx, right? Now, we know from grade 8, 9 about straight line equation, and we know that x is equal the independent values and y is equal the calculated or value of interest. And we know that a is the intercept and b is the slope of the line. We know those things. So it's a quick review there. And how do we calculate b? Now, this here little animal comes from what we call the method of least squares. So as long as you're going to calculate the slope of a line in statistics or in chemistry or in anywhere you have a set of observed values and it's a straight line, the method of least squares is most accurate. So this is not a regression that is in circles. It's called the method of least squares, right? So the method of least squares is used to calculate the slope of the line, where the slope of the line is b. Notice I just underlined that, right? And so the formula for calculating b using the method of least squares is that little animal in the circle, n sum of xy minus sum of x times the sum of y divided by n sum of x squared. So these little 2's are squared, right? Sum of x squared minus the sum of x squared, right? So again, this is just a little review because in terms of the formulas, because I expect that you would have come across them in your statistics. Where you have not, then it means that you have to put out a little more effort than those who would not have come across them to bring your knowledge up to speed. And I know you can do that, all right? So putting my faith in you there that you're going to do that. All right. So then, not only do we need to calculate b, which is the slope of the line, we need to calculate a, which is the intercept on the y-axis. So it's the sum of y minus b, sum of x over n. Yes, you can see the formula in different ways, in different text, or I know you guys like to go to YouTube. It's pretty much the same thing. It's just how it has been refined or not refined, right? How much work you are willing to put in to find the values of b and a. So if you see it somewhere else, written somewhere else, it doesn't mean that it is incorrect. It is simply just a refining of this basic initial formula. All right? Good. Now, so the Given the data below, as I said, the question here should be, which is the simple linear trend model that can be used to predict sales in the future? And why am I saying trend? Because the heading says week and sales. And I know that week is a part of how we say how time goes on or was recorded, and sales is the observed value that we would have recorded over this element of time. So once I'm seeing time as a part of the heading of the data, then I know that my instruction should say trend line. So the values for week would be my X values, and the values for sales would be my Y values. Some students tend to make the mistake of thinking that it is true that the values that are always first in the column is your X values. That's not true, so I'm warning you that that is not true. Read the heading of the table, in the data in the table, to ensure which is your X values and which is your Y values, all right? So we apply our formula. So here it is, the X squares that we need. We sum the weeks. We multiply our sales by the week, XY, sum of XY. And it's really just a matter of replacing the formulas. It's a matter of replacing the N, which is our number of data points, the sum of XY, the sum of X, and the sum of Y, finding the square of each X and summing it, and summing X and square it. So it's just a matter of doing that and replacing it in the formula. Oh, that minus should not be there. Where it says equal minus 315 over 50, it should just be 315. So no minus sign is there, right? So the B value, the slope of the line is 6.3, and the intercept on the line is 143.5. So the resulting trend line, now notice how I write the trend line? I have replaced all the letters with the information that pertains to the question. So here, Y, I've replaced it with sales. The A, I've replaced it with the value of 143.5. The B, I've replaced it with the value 6.3. And the X, I've replaced it with week because I am writing from the general to the specific. So when I look at this equation, I must see what it is the data is talking about, sales and week, and I must see the values that capture the progression of sales over the week that were recorded. So the equation must say something. It mustn't just be Y equals number X. It doesn't say anything, right? So please ensure that when you're writing your equations, it says something about the data that you have mined the information from. All right, so moving on. So this is our trend line. Now remember I said that the method of least squares is what we use to calculate the value of B and the value of X. It is the same method of least squares that we would use to calculate the value of B and the value of A in a regression. So once we know how to use the method of least squares in a trend line, we will also know how to use it in a regression. So again, all I have changed is the heading of one of the columns in the data. So where I had week, I now have number of competitors in a 5-mile radius. the sales heading remains. But notice how my equation now reads. It said sales equal the same values because I'm using the same information in terms of the data. 143.5 plus the 6.3, but the X is now not week, but number of competitors within a 5-mile radius. Good? All right, now, when we have calculated our equations, whether it's our trend line or our regression equation, usually our regression equation, we want to know some more information about those pieces of statistic that we have calculated and or manipulated and or observed. One piece of statistic that we are usually interested in is called the correlation coefficient, or R. You know, we love a shortcut. Common R. These days they use capital R or common R. It doesn't make a difference, right? We use the letter R to determine, or to denote rather, to denote our correlation coefficient. Now, the correlation coefficient is a quantity. It has no units attached to it. It measures two things. Notice, it measures the strength, 1, and 2, the direction of a linear relationship between two variables, right? And sometimes the complete name, you might see it called Pearson's product movement correlation coefficient, right? Pearson is the man who came up with it. So if you're upset about the work you have to do, go look for Mr. Pearson, right? And have a conversation with him. It's supposed to be a joke. All right, so the correlation coefficient, which sometimes we call Pearson's product moment correlation of coefficient, has values that fall between -1 and a +1. So the value that is used to represent the correlation coefficient will have a sign to it, either negative or positive, and it will have a number to it. The sign simply tells you which direction the relationship is going in. The number will tell you the strength. Now, how do you determine the strength? If the sign determines the direction, how do I use the number to tell me the strength? Well, it depends on how near or far that number is from 1. Now, remember, if it lies between -1 and +1. It means that the most R can be is 1. But usually it is some number under 1, which means it's usually a decimal. Now, the strength of the correlation is therefore determined by how near or far that decimal answer is from the figure 1. When you're determining strength, you do not look at the sign, you cover the sign. All you're concerned about is it near to 1 or is it far from 1? Right? When you have decided if it is near or far from 1, then you can say it's strong or it's weak, etc. So if it's near to 1, it's very strong. If it's far from 1, it's very weak, right? So you can look at the notes here and it tells you how to determine very strong or not strong, right? So as I said, near to 1, it's like 0.9 something, that's very strong because that's near to 1. If it's like 0.2, it's far from 1, so that's very weak, right? That's what I mean. Good? No. So here now, I'm saying here that the correlation coefficient can also be 0, right? So it can be positively correlated. And here's a picture of a positive correlation. It can be negatively correlated. Here's a picture of a negative correlation. And there can be no correlation, right? So again, the correlation tells you how near, no, sorry. The correlation tells you the strength and the direction of the relationship, right? So the sign tells you the direction, how near or far the value that you calculate the correlation to be is. That will, from 1, that will tell you the strength, right? Now, another piece of information that we often ask you about is the causation factor in the data under observation, right? So here is the formula for the correlation coefficient. Now, if you notice, it looks very much like the formula for B, the slope of the line, except you have 2 additions in the denominator. You have a square root sign, and you have another set of expression that looks like the expression in X, but their expression in Y on the right-hand side, over here. Over here. Ouch, sorry. Here. So you have inserted the square root, and you have another expression in Y in the denominator. But you have all of the information. The only new pieces of information that you will need in here is the Y squared. You have everything else. So when we ask you to calculate the correlation coefficient, it should be a hardship, because except for one piece of information, you have all the other bits of information already, right? So let me get this off of the page. Let me turn the page. So here I've calculated the correlation coefficient, and it's 0.98. So notice the same information that I used to calculate my B, same information I used to calculate my B, this, I had this, I had that, I had that. The only new piece of information in the formula is the starred information, which is the square your Y and sum it. So you have what it needs. The R is 0.98 and it's positive, meaning that's a very strong positive relationship. Good. Very strong positive relationship. So the 0.98 is very near to 1. And of course, you know that it's a positive sign. That implies there. No, the absence of sign implies it's a positive number, right? All right, so I said that there was another bit of information that we often require of you, and that is called the coefficient of determination, or R squared. It is literally taking the value of R and squaring it, right? R squared, or notice I said capital R, whichever of the two, right? So the coefficient of determination, R squared, which is taking R and multiplying it, so it's 0.98 times 0.98. We like to calculate it because it tells us the percentage of fluctuation or variation or changes that we can use the independent variable to explain the changes that we're seeing in the dependent variable, right? So note it says it is a measure that allows us to determine how certain one can be in making predictions from a certain model. So oftentimes we will ask the question, is this a good model? Once you see such a question, you're being asked to calculate the coefficient of determination. Now note that unlike the coefficient of correlation, the coefficient of determination lies between 0 and 1. So it's always positive. It's never negative. Does not carry a negative sign. The one that can carry the negative sign is the coefficient of correlation, right? But the coefficient of determination never carries a negative sign. And that's really just mathematics because you square the number, right? So again, it simply explains how confident you can be in making prediction from a certain model. How do we figure out how confident we can be? We look at the value of R squared, and we know that that value of R squared tells us when the independent value changes, what percentage of changes it will cause to appear in the dependent value. So 0.98 times 0.98. What is 0.98 times 0.98? Multiply that out for me. I never multiplied it out. 0.98 times 0.98. So I'm going to calculate that right now. 0.98 times 0.98 equals 0.96, right? So if I ask you to find R squared here, so if I ask you to find R squared, 0.98 times 0.98 is equal to 0.96. Or we can say 96%. So what does that mean? Simply means that 96% of the changes in our sales value can be explained by changes in the number of competitors within a 1 mile radius. So then, if we're able to say that 96% of the changes in the sales is because of changes in the number of competitors in the 1 mile radius, recall that our information just centers around sales observed and competitors observed. And that's the information that's in the model. It means then that 4% of the times when we see changes in our sales figure, it is because of some other element that was not captured in the model and cannot be explained by the changes in the number of competitors in the 1 mile or 5 mile radius, right? So the 4% remains unexplained, or it was not captured in the model. Whichever way you want to put it is acceptable, right? So then the R squared, which is a literal squaring of the R value, tells us that bit of information. It gives us confidence in determining when we make a prediction, how confident we can be, right? All right, that's quite a bit of a mouthful we just looked at, and we're still not finished. But for the most part, the theoretical underpinning that we need have been covered up to this point. I'm trying to erase the board again. So then, with that being said, we have now come to looking at the qualitative or the judgmental approach to forecasting. So we have looked at the quantitative elements, which are the ones that you're going to be asked to apply to your tutorial sheet. But you also need to know about the qualitative methods, right? So as we said, we tend to use the qualitative methods when we don't have sufficient quantitative data available and vice versa, right? Now, so we have multiple qualitative, meaning you're going to use your judgment, your knowledge, so on and so forth. But you can have some quantitative elements in there, but not enough to allow you to use, right? So one such method is what we call the Delphi method. And that method is used, it's a process that we use to gain consensus from among a group of experts. And notice that this process allows them to maintain their anonymity. They remain anonymous, right? Anonymity, right? And it's a forecasting technique that we applied to subjective demand for a product, right? And it's usually useful when you have no historical data, so you can't develop any statistical model. So what we have is the experts. The experts remain where they are in whichever part of the world, and they provide their estimates. And you have a coordinator who will send the questionnaire to these persons, and then they will collate the data, right? And so wherever you are in the world, nobody has to see or know you, because you have one person within the organization who will be in control of sending and receiving the data and collating the data. Okay? And when you come to some reasonable estimate, or questioning is what is reasonable, of course, then you can use that as a forecast. Sorry. Well, there you also, though it's not here, the Delphi method, a similar one to the Delphi method is the jury of executive opinions. The jury of executive opinions is similar to the Delphi method, except that where the Delphi method allows you to maintain your anonymity, right? Your anonymity. The jury, if you think about spy movies and movies where trial movies, jury are all sequestered in the same place. So in the jury of executive opinion, they're all at the same place. So the process is similar, but everybody knows everybody and who is saying what and who is doing what. So, but the process is similar. Then of course you have market research, right? And we have all come across people who approach us to say that they're doing market research, and can they have a conversation with us, and they're asking us questions and ticking off from their pre-prepared questionnaire. And you also probably would have done some market research as part of some of your project. So it's just a systematic way of approaching your external customers, to see the interest in your services or product, right? And you have some kind of hypothesis, and you go out and you gather the data and you try to prove or disprove your hypothesis, right? Again, it can be used to forecast demand for short, medium, and long term. And it is, they say it's fairly accurate, for short term, good for medium term, and has some use for the long term also. All right. So that therefore brings us to the end of the theoretical underpinning for our forecasting. It's way more than 1 hour, but that's why I recorded it, because I just want to get everything in, at least in terms of the theory, in one sitting. Now we still have another piece to do, which I will encourage your tutor to do in the tutorial, and that is the use of the Excel to construct your regression or your trend line model. I will try to do it in the lecture, but I need a desktop or a laptop, and I'm using what do you call these things again? Tablet. So I don't have the capability on my tablet, but somewhere or somehow you would go through that element either in the tutorials, or if I'm able to demonstrate it in the lecture, I will. So that takes me to the end of the forecasting lecture in terms of the presentation of the principles that you will need. Yes, there's much work to be done, and the tutorial sheet will take you through much more in depth, but this will at least give you a good starting point from which to be able to help yourselves to at least do up to question 5 on your tutorial sheet. All right. So I will see you later. I'm gonna post this one. Alrighty. Have a good evening. Bye.